Hi, and welcome to Programming Video Tutorials. This time, we're going to take a look at the C++ programming language, which is a general-purpose multi-paradigm language. C++ is an extension of the C language, and as such most C code can easily be made to compile in C++. Some of the major additions to C include object-oriented programming, operator overloading, multiple inheritance, and exception handling. The development of C++ started in 1979, 7 years after C first made its appearance. Despite being what many consider legacy languages, C and C++ are still the most widely used languages in the software industry. They're used in creating everything from operating systems and embedded software to desktop applications, games, and so on. Compared with newer languages, C++ applications are often more complex and take longer to develop. In return, C++ gives the programmer a tremendous amount of control in that the language provides both high-level and low-level abstractions from the hardware. It's also designed to give the programmer a lot of freedom by supporting many different programming styles. For example, using procedural, object-oriented, or generic programming. The compiler I'll be using in this tutorial is the Microsoft C++ compiler. Some other common ones include Borland's, Intel's, and GNU's compilers. Despite C++ being standardized in 1998, these compilers still support slightly different features, so I will point out when something applies specifically to Microsoft's compiler. To begin developing in C++, create an empty document with the CPP file extension and open it in the editor of your choice. In my case, I'll be using Visual Studio and have included the file in a new empty project. If you don't have Visual Studio, but would like to follow along in a similar environment, you can download Visual C++ Express from Microsoft's website. This is one of several free versions of this program. The first thing we'll add here is the main method. This is the entry point of the program, and the code inside the braces is what will be executed when the program runs. Our first application will simply output the text Hello World to the screen. Before we can do that, however, we need to include the IOStream header. This header provides input and output functionality to our program, and is one of the standard libraries that comes with all compilers. What the include directive does is effectively to replace the line with everything in the specified header before the file is compiled into an executable. If we're wondering what the header file contains, we can take a look at it by right-clicking on its name and selecting Open Document. Among other things in here, we can find out the exact location of the header. With the IOStream now included, we gain access to several new functions. These are all located in the standard namespace called std, which we can go inside using a double colon, also called the scope operator. In Visual Studio, the IntelliSense window will now automatically show up, displaying what the namespace contains. Among the members, we find the cout stream, which is the standard output stream in C++ that we use to print text to a console window. It uses two less than signs, known as the insertion operator, to indicate what to output. We can now write our string here, delimited by double quotes. After the statement, we place a semicolon, which is used in C++ to mark the end of all expression statements. If we want to make things a bit easier, we can add a line specifying that we're using the standard namespace. We then no longer have to prefix cout with the namespace, since it's now used by default. If we now try to run the application, the console window would close as soon as the main method was finished. To prevent this, we can add the get method, which belongs to the console input stream. This method reads input from the keyboard until the return key is pressed. We can now run the program by going up to Debug and clicking Start without debugging. Visual Studio then compiles and runs the application, which displays the text in the console window. When we then press the return key, the get method ends and thereby closes the program. As an alternative to using an IDE, we can also compile source files from the command line. To demonstrate, I've logged into a Linux server where I have uploaded this source file. From here, I can use the GNU C++ compiler, which is available on virtually all Unix systems. I type the compiler name G++ and give it the input and output file names as arguments. It then produces an executable, which when run gives the same result as the one compiled under Windows. Before we end this section, let's take a look at the two kinds of comment notations in C++, single line and multiline. These allow us to insert notes into our source code, and they will have no effect on the end program. Variables are used for storing data during program execution. Depending on what data we need to store, there are several different kinds of data types. In C++, the exact size and range of the data types aren't fixed. Instead, they are dependent on the system we compile for. The sizes shown in this table are those found on most 32-bit systems. By default, a char in C++ is 1 byte in size. A byte here is the minimum addressable unit of memory, which is guaranteed to be at least 8 bits, but might also be 16 or 32 bits depending on the system. The general specification is that the int type will have the same size as the system word. So for a 32-bit system, where the smallest addressable unit is 8 bits, the integers will be 4 bytes long. Each integer type in this table must also be at least as large as the one preceding it. The same applies to the floating point types, where each one must provide at least as much precision as the preceding one. To create a variable, we start with the data type we want it to hold, followed by an identifier, which is the name of the variable. In general, the name can consist of letters, numbers and underscores, but it cannot start with a number. Also, it cannot contain spaces or special characters, and it mustn't be a reserved keyword. We assign a value to the variable using the equal sign, which is the assignment operator. We can also combine the declaration and assignment into a single statement. At the same time that the variable is declared, we have an alternative way of initializing it by enclosing the value in parentheses. This is known as constructor initialization and is equivalent to the first method. If we need to declare more than one variable of the same type, there's a shorthand way to do this using the comma operator. As we see here, integers can also be assigned using octal and hexadecimal notation as well as standard decimal. All numbers here represents the same number, which in decimal notation is 50. Once we have a variable declared and initialized, we can then use it by simply referencing the variable's name. An important thing to keep in mind is that variables in C# are not initialized to 0 by default. Instead, they will contain whatever garbage is left in that memory location. It's therefore a good idea to always give your variables an initial value. There are 4 integer types we can use, depending on how large a number we need a variable to hold. Many C++ compilers also support the long data type, which is guaranteed to be at least 64 bits. To determine the exact size of a data type, we can use the sizeOf operator. This operator returns the number of bytes a data type occupies in the system we are compiling for. The Microsoft C++ compiler also features sized integer types. These types starts with 2 underscores, followed by int, and then the number of bits we want the integer to hold. By default, all the number types in Microsoft C++ are signed and may therefore contain both positive and negative values. If we know we only need to store positive values, we can declare them as unsigned to double their range. Signed and unsigned may also be used as standalone types, which is short for signed and unsigned int. The short and long data types are also abbreviated in this way. The floating point types can store real numbers with different levels of precision. They can also be assigned using the standard exponential notation. As for the precision shown here, it refers to the total number of digits in the number, so trying to assign more than 7 digits to a float means that the least significant ones will get rounded off. The character type is usually used to represent ASCII characters. The conversion between the number stored in the char and the character shown when we print it happens automatically. For another integer type to be displayed as a character, we have to explicitly cast it by placing char in parentheses before the variable. Finally, we have the Boolean type, which can only be either true or false. The numerical operators in C++ can be grouped into 5 types: arithmetic, assignment, comparison, logical, and bitwise operators. First, we have the 4 basic arithmetic operations, as well as modulus to get the division remainder. Notice that the division sign gives an incorrect result here. This is because it operates on 2 integer values, and will therefore truncate the result and return an integer. To get the correct value, we need to explicitly convert one of the numbers to a floating point number. A common use of the assignment and arithmetic operators is to operate on a variable and then to save the result back into that same variable. These operations can be shortened with the combined assignment operators. Another common operation is to increment or decrement a variable by 1. This can be simplified with the increment and decrement operators. Both of these can either be used before or after a variable. The result on the variable is the same whichever we use. The difference is that the post operator returns the original value before it changes the variable, while the pre-operator changes the variable first and then returns the value. Next, there's the comparison operators that compares 2 values and returns either true or false. Used together with these, we have the logical operators. Logical AND evaluates to true if both the left and right sides are true, and logical OR is true if either the left or right sides are true. To invert a Boolean result, we also have logical NOT. Note that for both logical AND and logical OR, the right-hand side won't be evaluated if the result is already determined by the left side. Lastly, we have the bitwise operators, which allows us to manipulate individual bits inside of an integer. For example, the OR operator makes the resulting bit 1 if the bits are set on either side of the operator. These bitwise operators also have shorthand assignment operators. Now let's look at operator precedence. In C++, expressions are normally evaluated from left to right. However, as we can see in this table, different operators also have different precedence that determine which one gets evaluated first. This same order applies to many other languages, such as Java and C# also. As an example, the logical AND operator binds weaker than the relational operators, which in turn binds weaker than the arithmetic operators. To make things clearer, we should instead use parentheses to decide what parts of the expression will be evaluated first, since parentheses has the highest precedence of all operators. A pointer is a variable that contains the memory address of another variable. We declare a pointer as we would any other variable, except that we prefix its name with an asterisk. The data type used determines what type of memory it will point to. If we now create a variable of that same type, we can make our pointer point to it by prefixing that variable with an ampersand to retrieve its address. This ampersand is called the address of operator. Our pointer p now contains the memory address of the variable I. To get the address stored in the pointer, we simply type its name, and to get the actual value stored in that address, we prefix the name with an asterisk, known as the dereference operator. Same thing when writing to the pointer. Without the asterisk, the pointer is assigned a new memory address, and with the asterisk, it will update the actual value of the variable it points to. If we create another pointer and assign it to p, it will then get a copy of p's memory address. Sometimes, however, we may want a pointer that can point to another pointer. This is done by declaring a pointer with 2 asterisks and then assigning it the address of the pointer we wanted to reference. This way, when the address in P changes, R can follow that change. Typing R now gives the address of P, dereferencing R gives the address of I, and dereferencing it again gives the value of I. One of the main usages of pointers is to allocate dynamic memory. Until now, we have only had as much memory available as we have declared for our variables. If we need any additional memory, we have to use the new operator. This operator allows for allocation of global memory, which can only be accessed through pointers. An important thing to know about dynamic memory is that it will not be released like the rest of the program's memory when it is no longer needed. Instead, we have to manually release it with the delete keyword when we're done using it. Forgetting to delete memory that we've allocated with a new keyword will give our program memory leaks, and that memory will stay allocated even when the program shuts down. A reference allows us to create an alternative name for a variable. We declare a reference just as we would declare a normal variable, except that we append an ampersand to the type name. At the same time as the reference is declared, it must also be initialized with a variable of the specified type. Otherwise, we will get a compile time error. Once the reference has been assigned, or seated as it's called, it can never be reseated with another variable. The reference has in effect become an alias for the variable, and we can now use it exactly as though we were using the original variable. A reference is similar to a pointer that always points to the same thing. However, while a pointer is a variable that points to another variable, a reference is only an alias and does not have an address on its own. Generally, whenever we don't need to reassign a pointer, we should use a reference instead, because a reference is safer than a pointer, since it must always refer to a variable. This means that we don't need to check if a reference refers to null, as we need to do with pointers. It is still possible for a reference to be invalid, for example, if the reference refers to a null pointer, but it's easier to avoid this kind of mistake with references than it is with pointers. Arrays are data structures used for storing a collection of values that all have the same data type. To declare an array, we begin as we would a normal variable declaration, but also append a set of square brackets. The bracket contains the number of elements in the array. The default values for these elements are the same as for variables. For global arrays, they become 0, and for local arrays, they are not initialized. To assign values to the elements, we can reference them one at a time by placing the element's index inside the square brackets, starting with 0. We can also assign values at the same time as the array is declared by enclosing them in curly brackets. The specified array length can then be left out to let the size be decided by the number of values assigned. Once the array elements are initialized, we can access them by referencing the index of the element we want. Arrays can also be made multidimensional by adding more sets of square brackets. As with single-dimensional arrays, they can either be filled in one at a time or all at once during the declaration. Because arrays are made up of non-dynamic memory, their size must be determined before execution. Therefore, the size needs to be a constant value. In order to create arrays with a variable length, we need to use dynamic memory, which is allocated with a new keyword and must be assigned to a pointer. Any array in C++ is actually a pointer to the first element in the array. The referencing of an array element can just as well be made with pointer arithmetics. By incrementing the pointer with 1, we move to the next element in the array, because changes to a pointer's address are implicitly multiplied by the size of their data type. Keep in mind that just like with any other pointer, it's possible to exceed the valid range of an array. It's therefore important to keep track of the array's length. To determine the length of a statically allocated array, we can use the sizeOf operator, but this cannot be used for dynamically allocated arrays. The only way to know the size of this array is through the variable that we used in its allocation. When we're done using a dynamic array, we must remember to delete it using the delete keyword with an appended set of square brackets. The string class in C++ is used to store string values. Before we can declare it, we need to include the string header, and we'll also include the standard namespace, since the string class is part of that namespace. We can now declare a string like any other data type. To assign it the text value, we delimit the literals by double quotes. Because the string data type is a class, we can also specify the initial value in a constructor, but only at the same time as we declare the string. To concatenate two strings, we can use the plus sign, known here as the concatenation operator. It also has an accompanying assignment operator to append a string. The concatenation operator will work as long as one of the strings it operates on is a C++ string. It does not work to concatenate two C strings or string literals. To do this, we have to explicitly cast them to strings. By leaving out the plus sign, string literals will also be concatenated implicitly. We can extend a string literal to more than one line by putting a backslash sign at the end of each line. If we want to add a new line into the string itself, we instead use the escape character \n. This backslash notation is used to write special characters, such as a tab or form feed character. Additionally, we can express any one of the 128 ASCII characters by writing a backslash followed by the ASCII code, expressed as either an octal or hexadecimal number. The way to compare two strings is simply by using the equal operator. This will not compare the memory addresses, as it does with C strings. The conditional statements in C++ allow us to execute different code blocks based on different conditions. The if statement will execute only if the expression inside the parenthesis is validated to true. In C++, this does not have to be a Boolean expression. It can be anything that evaluates to a number, in which case 0 is false and all other numbers are true. To test for other conditions, we can extend the if statement with any number of else-if clauses. We can also have one else clause at the end, which will execute if all previous conditions are false. As for the curly brackets, they can be left out if we only need to execute a single statement conditionally. Next we have the switch statement, which checks for equality between an integer and a series of case labels, and then passes execution to the matching case. It may contain any number of case clauses, and it can end with a default label for handling all other cases. Note that the statements after each case label end with a break keyword to skip the rest of the switch. If we leave out the break, execution will fall through to the next case, which can be useful if several cases needs to be evaluated in the same way. In addition to the if and switch statements, there's the ternary operator that can replace a single else-if clause when it assigns values to a variable. This operator takes three expressions. If the first one is evaluated to true, the second expression is returned, and if it's false, the third one is returned. The expressions can be any statements that return values. For example, we can let the expressions contain the assignments themselves, in which case the assigned value will be returned. There are three looping structures available in C++, all of which are used to execute a specific code block several times. The while loop runs through the code block only if its condition is true, and will continue looping for as long as the condition remains true. Note that the condition is only checked at the beginning of each iteration. Next there's the do-while loop that works the same as the while loop, except that it checks the condition after the code block, and will therefore always run through the code block at least once. Keep in mind that this is the only loop that ends with a semicolon. The for loop is used to go through a code block a specific number of times. It takes three parameters. The first one initializes a counter and is always executed once before the loop. The second parameter holds the condition for the loop and is checked before each iteration, and the third parameter contains the increment to the counter and is executed at the end of each loop. The for loop also has several variations. For starters, the first and third parameters can be split into several statements using the comma operator. We also have the option of leaving out any one of the parameters. These are the three looping structures in C++. Just as with the conditional statements, the braces can be left out if there's only one statement in the code block. There are two jump statements that can be used inside of loops. The break keyword, which ends the current loop, and continue, which skips the rest of the current loop and continues at the beginning of the next iteration. A third jump statement that may be good to know about is goTo, which performs an unconditional jump to a specified label. This instruction is generally never used since it tends to make the flow of execution difficult to follow. A function is a reusable code block that will execute only when it's called. To create one, we'll start by typing void, followed by the function's name, an optional parameter list, and a code block. The void keyword simply says that this method will not return a value. The naming convention for functions is the same as for variables, a descriptive name with each word initially capitalized except for the first one. This method here will simply print out a text message. To invoke it from the main method, we type the method's name followed by a set of parentheses. The parentheses are used to pass arguments to the function. To pass arguments, we must first add them to the function declaration in the form of a comma-separated list. A function can take any number of arguments, and they can have any data types. We just need to make sure to call the function with the same type and number of arguments. We can specify a default value for an argument by assigning it a value inside of the parameter list. Now, if we don't specify that argument when calling the method, the default value will be used instead. For this to work, it's important that the arguments with default values are to the right of the arguments with no default values. A function in C++ can be defined multiple times with different arguments. This is a powerful feature called method overloading, which allows a method to handle a variety of parameters transparently to the programmer using the method. A function can also be used to return a value. We then replace the void keyword with the data type we want the function to return, and add the return keyword to the function's body, followed by an argument of the specified return type. Return is a jump statement that causes the current function to exit and return the specified value to the place where the method was called. We can here, for example, pass the return value as an argument to the output stream, since the function now evaluates to an integer. If we want to, we can also use the return keyword in the void function to exit before the end block is reached. Note that although the main method is set to return an integer type, we do not have to explicitly return any value. This is because the compiler will automatically add a return 0 statement to the end of the main method. An important thing to keep in mind in C++ is that functions must be declared before they can be called. This does not mean that we have to implement the function before it is called. It only means that we need to specify the function's header in the beginning of the source file so that the compiler knows that the function exists. This kind of forward declaration is known as a prototype. The argument names in the prototype does not need to be included. Only the data types must be specified. In C++, both fundamental and object data types are by default passed by value. This means that only a copy of the value or object is passed to the function. Therefore, changing the argument in any way will not affect the original, and passing a large object will be very slow. To instead pass a variable by reference, we just need to add an ampersand before the argument's name in the function's definition. When passing arguments by reference, both fundamental and object data types can be changed or replaced, and the changes will affect the original. As an alternative to passing by reference, we may also pass arguments by address using pointers. This passing technique serves the same purpose as passing by reference, but uses pointer syntax instead. In addition to passing variables by value, reference, or address, we may also return a variable in one of these ways. Most commonly, we want a function to return by value, in which case a copy of the value is returned to the caller. To instead return by reference, we place an ampersand after the function's return type. The function must then return a variable, and may not return an expression or literal as can be done when using return by value. The variable returned should never be a local variable, since the memory to these variables are released when the function ends. Instead, we commonly use return by reference to return an argument that has also been passed to the function by reference. To return by address, we append the dereference operator to the function's return type. This return technique has the same two restrictions as when returning by reference. We must return the address of a variable, and the returned variable must not be local to the function. A thing to keep in mind when using functions is that every time a function is called, a performance overhead occurs. To potentially remove this overhead, we can recommend that the compiler inlines the calls to a specific function by using the inline keyword. This keyword is best suited for small functions that are called inside of loops. It should not be used on larger functions, since inlining these can severely increase the size of the code, which instead decreases performance. Note that the inline keyword is only a recommendation. The compiler may, in its attempt to optimize the code, choose to ignore this recommendation, and it may also inline functions that do not have the inline modifier. A class is a template used to create objects. To define one, we use the class keyword followed by a name, a code block, and a semicolon. The naming convention for classes is mixed case, that is, each word should be initially capitalized. Inside of the class, we can declare class members, the main two of which are fields and methods. Fields are variables that holds the state of the object, while methods define what the object can do. A method belonging to a class is normally declared as a prototype inside of the class, and the actual implementation is placed after the class's definition. The method's name outside of the class then needs to be prefixed with the class name and the scope resolution operator in order to designate which class the method definition belongs to. If the method is short and we want to recommend to the compiler that the code should be inlined, one way to do this would be to use the inline keyword in the method's definition. A more convenient way is simply to define the method inside of the class. This will implicitly recommend to the compiler that the method should be inlined. Our class definition is now complete. In order to use it, we first have to create an instance of the class, which is also called an object. This can be done just as we declare any other variable. Before we can access the members that this object contains, they first need to be declared as public, using the public keyword followed by a colon in the class definition. We can now access both the fields and methods for this object using the dot operator after the instance name. Note that we can create any number of objects based on a class, and each one of them will have its own set of fields and methods. Classes, just as functions, must be declared before they can be referenced. If we have circular references, such as in this example, then changing the order that the classes are defined in will not solve the problem. Instead, what we need to do in this situation is to declare a class prototype. This prototype declaration allows us to reference the class before it is defined, for example, as we do here using a pointer. However, even with a prototype, we still cannot create an object of a class before it has been defined. In addition to fields and methods, a class can also contain a constructor. This is a special kind of method used to initialize the object. It always has the same name as the class, and it doesn't have a return type. To be accessible from another class, the constructor needs to be declared in a section marked with a public access modifier. When we create a new instance of this class, the constructor method is called, which here sets the two fields to some default values. Note that when creating an object using the noParameter constructor, as we do here, the assignment part can optionally be left out, as we have done before, but to pass arguments to the constructor, we have to include it. Just as with any other method, we can overload the constructor with different parameter lists. For example, with these two constructors, we can now initialize the object either with no arguments or with two arguments, which will be used to assign the fields. Inside of the constructor, as well as in other methods belonging to the object, we can use a special keyword called this, which is a pointer to the current instance of the class. If we, for example, use the same parameter names as the field names, we could still access the fields by using the this pointer, even though they are overshadowed by the arguments. As an alternative to assigning fields inside of the constructor, they may also be assigned using the constructor's initialization list. This list starts with a colon after the parameter list and is followed by calls to the field's own constructors. This is actually the recommended way of assigning all fields, because it gives better performance than assigning them inside of the constructor. If we don't define any constructors for a class, the compiler will then automatically create a default constructor with no parameters when the program compiles. Because of this, we can instantiate the class even without implementing a constructor. The default constructor will only allocate memory for the object. It will not initialize the fields. Fields in C++, just as with local variables, are never assigned default values automatically. Instead, they will contain whatever garbage is left in that memory location until we explicitly assign them values. Inheritance enables a class to reuse code from other classes. In this example, we would like the class square to inherit from rectangle. This is specified after the class name with a colon followed by the public keyword and the name of the class we wish to inherit from. Rectangle now becomes a base class of square, which in turn becomes a derived class of rectangle. In addition to its own members, square gains all accessible members in rectangle, except for its constructors and destructor. Because square is now a kind of rectangle, it can be used anywhere a rectangle would be expected. For example, we can pass a square as an argument to a function that expects a rectangle, since the square class contains everything in the rectangle class. Inside the function, the square is viewed as a rectangle, so we can only access the rectangle members. A new method in a derived class can redefine a method in a base class in order to give it a new implementation. To demonstrate this, we'll redefine rectangle's getArea method by redeclaring it in triangle with the same signature. The signature includes the name, parameter list, and return type of the method. If we now create a triangle and invoke the getArea method, triangle's version will get called. However, if we upcast the triangle to a rectangle, we will instead call rectangle's version. This is because the redefined method has only hidden the inherited method. That is, triangle's implementation is redefined downwards in the class hierarchy to any child classes of triangle, but not upwards to the base class. In order to redefine a method upwards in the class hierarchy, what is called overriding, the method needs to be declared with a virtual modifier in the base class. This modifier simply allows the method to be overridden in derived classes. calling the getArea method from rectangles interface will now also invoke triangles implementation. It is still possible to access a redefined method from a derived class by typing the class name followed by the scope resolution operator. This is called base class scoping and can be used to allow access to redefined methods that are any number of levels deep in the class hierarchy. Another place where this is important is in the constructors of derived classes. Base class constructors in C++ are not implicitly called by derived constructors as they are in C# and Java. Instead, they need to be explicitly invoked from the beginning of the derived constructor's initialization list in order to construct the base class. Note that we here don't have to qualify the base constructor with a class name, since this is implicit. Every class member has an accessibility level which determines where that member will be visible. There are 3 of them available in C++: public, protected, and private. The default access level for class members is private. To change the access level, we use an access modifier followed by a colon. Every field or method that comes after this label will now have this access level until another access level is specified or until the class declaration ends. To show the differences between the access levels, let's define one field for each level. If we try to access the fields within the containing class, we can see that all members, regardless of their access level, are accessible in the class where they are declared. This is the only place where the private member can be accessed. A protected member can also be accessed from inside of a derived class, but it cannot be reached from an unrelated class. The last access level is public, which gives unrestricted access from anywhere in the code. If we want to allow a class to access the private and protected members of another class, we can declare the class as a friend. The friend is allowed to access all members in the class where the friend is defined, but not the other way around. A global function can also be declared as a friend to a class in order to gain the same benefits. When a class is inherited in C++, it is possible to change the access level of the inherited members. Public inheritance lets all members keep their original access level. Protected inheritance reduces the access of public members to protected, and private inheritance restricts all inherited members to private access. Private is the default inheritance level, although public inheritance is used most frequently. The static keyword is used to create class members that exist in only one copy, which belongs to a class itself, and that are shared among all instances of the class. This is different from instance members, which are created as new copies for each new object. A static or class variable cannot be initialized inside of the class like an instance variable. Instead, it must be defined outside of the class declaration. This initialization will only take place once, and the static field will then remain initialized throughout the life of the application. To access a static member from outside of the class, the name of the class is used, followed by the scope resolution operator and the static member. This means that we don't have to create an instance of the class in order to access static members. In addition to fields, methods can also be declared as static, in which case they too can be called without having to define an instance of the class. However, because the static method is not part of any instance, it cannot use any instance members. Methods should therefore only be declared static if they perform a generic function that is independent of any instance variables. Note that instance methods, in contrast to class methods, can use both static and instance members. Local variables inside of a function can also be declared as static to make the function remember the variable. A static local variable is only initialized once when execution first reaches the declaration, and that declaration is then ignored every subsequent time execution passes through. One last place where the static keyword can be applied is to global variables. This will limit the accessibility of the variable to only this source file and can therefore be used to help avoid naming conflicts. An enumeration is a user-defined type consisting of a fixed list of named constants. For example, we here have an enum type called color containing 3 constants, red, green and blue. This color type can now be used to create a variable that can hold any one of these constant values. To assign one of them to the variable, we can simply type the name of the constant. In order to avoid naming conflicts, we can also qualify the constant with the name of the enum. The switch statement provides a good example of when enumerations can be used. Compared to using ordinary constants, the enumeration has the advantage that it allows us to clearly specify what values a variable should contain. Usually, we don't need to know the underlying values that the constants represent, but in some cases it can be useful. By default, the first constant in the enum list has the value 0, and each successive constant has one value higher. We can override these default values by assigning the constants to any values we want. These values can be computed and don't have to be unique. The compiler can implicitly convert an enumeration constant to an integer. However, assigning an integer back into an enum requires an explicit cast, since this conversion makes it possible to assign a value to the variable that is not included in the enum list. Note that an enum does not have to be declared globally. It can also be placed within a class as a class member, or even be defined locally in a function. A struct in C++ is equivalent to a class, except that members of a struct default to public access instead of private access as in classes. By convention, a struct is used instead of a class when we want to represent a simple data structure that mainly contains public fields. To declare objects of a struct, we can use the normal declaration syntax as we have seen before. Another alternative syntax commonly used with structs is to declare the objects when the struct is defined by placing the object names before the ending semicolon. There is also a syntactical shortcut available when we want to initialize an object, which is called aggregate initialization. This allows us to set the fields using a brace-enclosed, comma-separated list of initializer clauses. This type of initialization can only be used when the class type does not include any constructors, virtual functions, or base classes. The fields must also all be public, unless they are declared as static. This is why it is more common to use aggregate initialization with structs than it is with classes. Similar to structs, C++ also has the union type, which has the difference that all fields share the same memory position. Therefore, the size of a union is the size of the largest field it contains, in this case the integer field, which is 4 bytes large. This means that the union type can only be used to store one value at a time, because changing one field will also change the value of the others. The benefit of a union, in addition to efficient memory usage, is that it provides multiple ways of viewing the same memory location. For example, we can declare a union with 3 data members that allow us to access the same group of 4 bytes in multiple ways. Using the integer field, we can access all 4 bytes at once. Using the data structure, we can view 2 bytes at a time, and using the char array, we can view just a single byte. A union type can also be declared without a name. This is called an anonymous union and defines an unnamed object whose members can be accessed directly from the scope where it's declared. An anonymous union cannot contain methods or non-public members, and if it's declared globally, it must be static. Operator overloading allows operators to be redefined and used where one or both of the operands are of a user-defined class. When done correctly, this can simplify the code and make user-defined types as easy to use as the fundamental types. As we can see in this example, we have a class called minum with an integer field called val and a constructor for setting that field. We also have an addition method that adds two minum objects together and returns the result as a new object. If we create two instances of minum, we can add them together using this method. What operator overloading does is allow us to simplify this syntax and thereby provide a more intuitive interface for our class. To convert the add method to an overload for the addition sign, we replace the name of the method with the operator keyword followed by the operator we want to overload. The white space between the keyword and the operator can optionally be left out. Since the class now overloads the addition sign, we can use this operator to perform the needed calculation. Keep in mind that the operator is only an alternative syntax for calling the actual method. Addition is a binary operator, that is, it takes two operands. The first operand is the object from which the method is called, and the second operand is what is passed to the method. When we overload a unary operator, such as the prefix increment, we do not need a method parameter, since these operators only affect the object from which they are called. With the unary operators, we should always return a reference of the same type as the object. This is because when using a unary operator on an object, we expect the result to give us back the same object and not just a copy. On the other hand, when using a binary operator, we expect a copy of the result to be returned, and therefore we return by value. Not all unary operators should return by reference. The two postfix operators, increment and decrement, should instead return by value, because the postfix operations are expected to return the state of the object before the increment or decrement occurs. Note that to distinguish the postfix from the prefix operators, they have an unused integer parameter specified. C++ allows overloading of almost all operators in the language. As we can see in this table, most operators are of the binary type. Only a couple of them are unary, and some special operators cannot be categorized as either one. There are also some operators that can't be overloaded at all. In this section, I'm going to show you how to define custom type conversions for an object. As we can see here, we have a class called minum with a single integer field. What we want to do in this example is to allow integer types to be implicitly converted to the object's type. For this to work, we simply need to add a constructor that takes a single parameter of the desired type, in this case an int. Now, when that type is assigned to an object of the class, then that constructor will implicitly be called to perform the type conversion. This means that any constructor that takes exactly one argument can be used both for constructing an object and for performing implicit type conversions to that object type. These conversions will not only work for the specific parameter type, but also for any type that can be implicitly changed into it. In this case, the char can be implicitly converted to an int, and therefore can also be changed into a minum object. If we want to help prevent potentially unintended object type conversions, it's possible to disable the second use of the single parameter constructor. The explicit constructor modifier is then applied, which specifies that the constructor may only be used for object construction and not for type conversion. We must therefore use explicit constructor syntax here when we want to create a new object. Namespaces are used to avoid naming conflicts by allowing us to group entities such as classes and functions under a separate scope. In this example, we have two classes that belong to the global scope. Because they both share the same name and scope, this code will not compile. One way to solve this problem would be to rename one of the conflicting classes. Another solution is to group one or both of them under a different namespace by enclosing each in a namespace block. The classes now belong to different scopes, and so there is no longer a naming conflict. To access a member of a namespace from outside of that namespace, we need to specify the member's fully qualified name. This means that we have to prefix the member name with the namespace it belongs to, followed by the scope resolution operator. To further structure the program entities, it's possible to nest namespaces any number of levels deep. We just need to be sure that we qualify the nested namespace members with a full namespace hierarchy. If we don't want to have to specify the namespace every time we use one of its members, we can import the namespace into the global or local scope with the help of a using declaration. This declaration includes the using namespace keywords, followed by the namespace to be imported. It can be placed either locally, where it will only have effect until the end of the code block, or it can be placed in the global scope, where it will affect the code in the source file that follows its declaration. Keep in mind that importing a namespace into the global scope defeats the main purpose of using namespaces, which is to avoid naming conflicts. Such conflicts, however, are mainly an issue in projects that use several independently developed code libraries. If we don't want to have to type the fully qualified name, but also don't want to import the whole namespace, we can instead import only the specific members that we need from the namespace. This is done one member at a time with the using keyword, followed by the fully qualified namespace member that we want to import. Another thing we can do to shorten the fully qualified name is to create a namespace alias. The namespace keyword is then used, followed by an alias name, to which we assign the fully qualified namespace. This alias can then be used instead of the namespace qualifier that it represents. Note that both the namespace member imports and the namespace aliases may be declared both globally and locally. Finally, remember that in C++, merely importing a namespace does not provide access to the members included in that namespace, unless they are defined in the current source file. In order to access the namespace members, the prototypes also have to be made available, for example, using the appropriate include directives. In general, it's a good idea to always declare variables as constant if they don't need to be modified, because this makes sure that they won't be changed anywhere in the program by mistake, which in turn helps to prevent bugs. A variable in C++ can be made into a constant by adding the const keyword either before or after the data type. This modifier means that the variable becomes read-only, and it must therefore be assigned a value at the same time as it's declared. Attempting to change the value will now result in a compile time error. When it comes to pointers, const can be used in two ways. First, the pointer can be made constant, which means that it can't be changed to point to another location. And second, we can declare that the pointee is constant. This means that the variable pointed to cannot be modified through this pointer. It is also possible to declare both the pointer and the pointee as constants to make them both read-only. Note that the constant variables may not be pointed to by a pointer to a non-constant type. This prevents us from accidentally rewriting a constant variable using a pointer. References can also be declared as constant in the same way as pointers. However, since reseating a reference is never allowed, declaring the reference as const would be redundant. It only makes sense to protect the referee from change. Just as with variables, pointers, and references, objects can also be declared as constant. This not only prevents us from accidentally reassigning the object to another instance, it also prevents us from changing the fields that the object contains. Because of this restriction, a constant object may not call a non-constant method, since these methods are allowed to change the object's fields. They may only call constant functions, which are methods that are marked with a const modifier just before the method body. This const modifier means that the method is not allowed to modify the state of the object and can therefore safely be called by a constant object of the class. More specifically, the const modifier applies to the this pointer that is implicitly passed to the function. This effectively restricts the method from modifying the object's fields or calling any non-constant methods in the class. Note that in addition to making the method constants, the return type and method parameters may also be made read-only. For example, if we wanted to return a field by reference instead of by value from a constant function, we must make sure that it is returned as a constant in order to maintain the constantness of the object. Note that not all C++ compilers will be able to catch this subtle mistake. Static and instance fields in a class can also be declared as constant. A constant, non-static field must be assigned its value using the constructor's initialization list. This is the same as the preferred way of initializing non-constant, non-static fields. A constant static field, on the other hand, must be defined outside of the class declaration, the same way as with non-constant static fields. The exception to this is if the constant static field is of an integer data type. Such a field may also be initialized within the class at the same time as the field is declared. The preprocessor is a program invoked by the compiler that modifies the source code before the actual compilation takes place. This modification is done according to the preprocessor directives that we include in our source files. The directives are easily distinguished from normal programming code in that they all start with a hash sign. They must always appear as the first non-whitespace character on a line. The first directive we'll look at is include, which inserts the content of a specific file into the current one. If the file name is enclosed between angle brackets, the compiler will search for the file in the default directory where it is configured to look for the standard header files. If we instead specify the file name between double quotes, the compiler will first search for the file in the same directory as the source file, and in case it's not there, it will then search among the standard header files. We can also use the double quotes to specify an absolute or relative path to the file that we want to include. Another important directive is define, which is used to define macros. We first specify the name of the macro, followed by what we want it to be replaced by. The preprocessor will then go through and change any occurrences of the macro with whatever comes after it in its definition until the end of the line. By convention, the macro should be named in uppercase, with each word separated by an underscore. That way, they are easy to spot when reading the source code. A define directive shouldn't be used to override a previously defined macro directly. Doing so will give a compiler warning. In order to change a macro, we first need to undefine it using the undef directive before we redefine it. Note that we do not get a warning for attempting to undefine a macro that is not currently defined. A macro can, if we want to, be made to take arguments. This allows us to create compile time functions. For example, we here have a macro function that evaluates to the maximum of 2 values. To use it, we just need to call it as if it was a normal C++ function. Keep in mind that for this kind of function to work, we may only use arguments that are known at compile time. If we want to break a macro function across several lines, we can do so using the / symbol. This will escape the new line character that marks the end of a preprocessor directive. As a final note, I want to point out that although define directives can be powerful, they also tend to make the code more difficult to read and debug. Define should therefore only be used where it is absolutely necessary. C++ code, such as constant variables, enums, and inline functions, can often accomplish the same goal more efficiently and safely than define directives can. Next up, we're going to look at the directives used for conditional compilation. These directives let us include or exclude part of the source code if a certain condition is met. First, we have the if and endif directives, which specifies a section of code that will only be included if the condition after the if directive is true. Note that this condition must evaluate to a constant expression. Just as with the C++ if statement, we can optionally include any number of else if or elif directives and one final else directive. Sometimes we may want to compile a section only if a certain macro has been defined, irrespective of its value. We can then use 2 special operators, which are defined and not defined. The same effect can also be achieved using the directives if defined and if not defined, respectively. For example, the if defined section is only compiled if the specified macro has been previously defined. Note that the macro is considered defined even if it has not been given a value. Next, we have the error directive, which aborts the compilation when found. This directive can be useful, for example, to determine if a certain line is being compiled or not. The directive can optionally take a parameter that specifies the description of the generated compilation error. Another standard directive is line, which allows us to change the line number that is displayed when an error occurs during compilation. Following this directive, the line number will as usual be increased by 1 for each successive line. The directive can also take an optional string parameter that allows us to change the file name that will be shown when an error occurs. The last standard directive is pragma, or pragmatic information. This directive is used to specify options to the compiler. For example, we can use pragma message to have the compiler output a string to the build window, or pragma warning to change how the compiler handles warnings. Exception handling allows us to deal with unexpected situations that may occur in a program. When a function encounters a situation that it cannot recover from, it can generate an exception to signal to the caller that the function has failed. This is done using the throw keyword, followed by whatever it is we want to signal. When this statement is reached, the method will stop executing, and the exception will propagate up to the caller, where we can catch it using a try-catch statement. This statement consists of a try block containing code that may cause exceptions, and one or more catch clauses to handle them. In this case, we throw an integer, and so we need to include one catch block that handles this type of exception. The thrown expression will get passed as an argument to the exception handler, where it can be used to determine what has gone wrong with the function. Note that when the exception has been handled, the execution will then continue running after the try-catch blocks, and not after the throw statement. An exception handler can catch a thrown expression either by value, reference, or pointer. However, catching by value should be avoided, since this causes an extra copy to be made. Catching by reference is generally preferable. If the code in the try block can throw more types of exceptions, we will need to add more catch clauses to handle them. Keep in mind that only the handler that matches the thrown expression will be executed. To catch all types of exceptions, we can use an ellipsis as the parameter of catch. This default handler must be placed as the last catch statement, since no handler placed after it would ever be executed. If an exception handler is not able to recover from an exception, we can then rethrow it using only the throw keyword to pass it along to an external try-catch block. Be careful though, because if an exception is never caught, the program will terminate with a runtime error. Functions are by default allowed to throw exceptions of any type. To specify the exception types that a function may throw, we can append the throw keyword to the function declaration, followed by a comma-separated list of the allowed types, if any, enclosed in parentheses. This exception specification is very different from the one used in Java, and overall there is very little reason to specify exceptions in C++. The compiler will not enforce the specified exceptions in any way, and it will not be able to make any optimizations because of them. As previously mentioned, any data type can be thrown in C++, but the standard library does provide a base class called exception, which is specifically designed to declare objects to be thrown. It is defined in the exception header file and is located under the std namespace. As seen here, it can be constructed with a char sequence that becomes the exception's description. When we catch this exception, we can use the object's function what to retrieve the description. Converting an expression from one type to another is known as type conversion. This can be done either implicitly or explicitly. An implicit conversion is performed automatically by the compiler when an expression needs to be converted into one of its compatible types. For example, any conversions between the fundamental data types can be done implicitly. These fundamental implicit conversions can further be grouped into two kinds, promotion and demotion. Promotion occurs when an expression gets implicitly converted into a larger type, and demotion when converting an expression to a smaller type. Because a demotion can result in the loss of information, these conversions will on most compilers generate a warning. If the potential information loss is intentional, we can suppress this warning by using an explicit cast. The first explicit cast we'll look at is the one inherited from C, commonly called the C-style cast. We simply place the desired data type in parentheses to the left of the expression that we want to convert. This cast is suitable for most conversions between the fundamental data types. However, when it comes to conversions between classes and pointers, it can be too powerful. In order to get more control over the different types of conversions that are possible, C++ introduced the four new style casts. These are static, reinterpret, const, and dynamic cast. Their format is to follow the cast name with a new type enclosed in angle brackets, and thereafter the expression to be converted in parentheses. These casts allow us to more precisely state how a conversion should be performed, which in turn makes it easier for the compiler to catch conversion errors. In contrast, the C-style cast includes the static, reinterpret, and const cast all in one operation, and we're therefore more likely to perform subtle conversion errors when using it. The first new style cast we'll look at is the static cast. This one simply performs conversions between compatible types. It is similar but more restrictive than the C-style cast. For example, the C-style cast would allow an integer pointer to point to a char. Since this gives us a 4-byte pointer pointing to 1 byte of allocated memory, writing to this pointer will either cause a runtime error or it will override some adjacent memory on the stack. In contrast to the C-style cast, the static cast will allow the compiler to check that the pointer and pointee data types are compatible, which allow us to catch this incorrect pointer assignment during compilation. If we wanted to force the pointer conversion in the same way as the C-style cast did in the background, we would instead use a reinterpret cast. This cast handles conversions between certain unrelated types, such as from one pointer type to another incompatible pointer type. It will simply perform a binary copy of the data without altering the underlying bit pattern. Note that the result of such a low-level operation is system-specific and therefore not portable. It should be used with caution if it cannot be avoided altogether. The third C++ cast is the const cast. This one is primarily used to add or remove the const modifier of a variable. Note that although this allows us to change the value of a constant, doing so is still invalid code that may cause a runtime error. For example, if the constant was located in a section of read-only memory. Constcast is instead used mainly when we have a function that takes a non-constant pointer parameter, even though it does not modify the pointee. We can then pass this function a constant variable by using the const cast. Keep in mind that the C-style cast can also remove the constant modifier, but again, since it does this conversion behind the scenes, the C++ cast is preferable. Another reason to use the C++ casts is that they are easier to search for in the code than the C-style cast. This is important because casting errors can be difficult to discover. The fourth and last C++ cast is dynamic cast. This one is only used to convert object pointers and object references into other pointer or reference types in the inheritance hierarchy. It is the only cast that makes sure that the object pointed to can be converted by performing a runtime check that the pointer refers to a complete object of the destination type. For this runtime check to be possible, the object must be polymorphic. That is, the class must define or inherit at least one virtual function, because the compiler will only generate the needed runtime type information for such objects. In the first example, we convert a mychild pointer into a mybase pointer using a dynamic cast. This derived-to-base conversion succeeds because the child object includes a complete base object. In the next example, we instead attempt to convert a mybase pointer to a mychild pointer. Since the base object does not contain a complete child object, this pointer conversion will fail, and to indicate this, the dynamic cast returns a null pointer. This gives us a convenient way to check if a conversion has succeeded or not during runtime. If we did not convert a pointer, but a reference instead, the dynamic cast would fail by throwing a bad cast exception, which we would need to handle using a try-catch statement. Note that the advantage of using a dynamic cast is that it allows us to check if a conversion has succeeded during runtime. The disadvantage is that there is a performance overhead associated with doing this check. For this reason, using a static cast would have been preferable in the first example, because the derived-to-base conversion will never fail. However, in the second example, the conversion may either succeed or fail. It will fail if the mybase object contains a mybase instance, and it will succeed if it contains a mychild instance. In some situations, we may not know which one it contains until runtime. In that case, a dynamic cast would be a better choice than static cast. If we had performed the base-to-derived conversion using a static cast instead of a dynamic cast, the conversion would not have failed. It would have returned a pointer that referenced an incomplete object, and dereferencing such a pointer can lead to runtime errors. Templates provide a way to make a class or function operate with different data types without having to rewrite the code for each type. First, we'll look at function templates. In this example, we have a function that swaps two integer arguments. To make this method into a function template that can work with any type, we first need to add a template parameter declaration before the function. This declaration includes the template keyword, followed by the keyword class and the name of the template parameter, enclosed between angle brackets. Alternatively, the keyword typename can be used instead of class. They are both equivalent in this context. The name of the template parameter may be anything we want, but it's common to name it with a capital T. The second thing we need to do to complete the function template is to replace the data type that we want to be made generic with our template parameter. We now have a complete function template. To use it, we can call swap as if it was a regular function, but with our desired template parameter specified in angle brackets before the function parameters. Behind the scenes, the compiler will instantiate a new function with this template parameter filled in, and it is this generated function that will be called from this line. Whenever we use the template function with a new type, the compiler will instantiate another function using the template. In this case, we may also call the function template as if it was a regular function without specifying the template parameter. This is because the compiler can automatically deduce the type, since the function template's argument uses the template type. However, if this was not the case, or if we wanted to force the compiler to select a specific instantiation of the function template, we would then need to explicitly specify the template parameter within angle brackets. Templates can also be defined to accept more than one template parameter just by adding them between the angle brackets. In this example, the second template parameter allows us to call the swap method with two arguments of different types. Class templates allow class members to use template parameters as types. They are created in the same way as function templates, but unlike function templates, a class template must always be instantiated with a template parameter explicitly specified. Another thing to remember when using class templates is that if we define a method outside of the class template, we must then also precede the definition with a template declaration. Note that the template parameter between the angle brackets after the class name specifies that the function's template parameter is the same as the class's template parameter. In addition to type parameters, templates can also have regular function-like parameters. As an example, we can add an integer parameter that is used to decide the size of an array. When we now instantiate this class template, we have to include both a type and an integer. Similar to function arguments, template parameters can also be given default values and types. To use these defaults, we just need to leave the angle brackets empty when instantiating the class template. If we want to define a different implementation for a template when a specific type is passed as template parameter, we can declare a template specialization. For example, in this class template, there is a print method that outputs the variable a. Say that when the template parameter is a bool, we would like it to print out true or false instead of 1 or 0. One way to do this would be to create a class template specialization. We then create a re-implementation of the class template where the template parameter list is empty. Instead, we place a bool specialization parameter after the class template's name, and we use this data type instead of the template parameter throughout the implementation. When we now instantiate the class template with a Boolean template type, this template specialization will be used instead of the standard one. Note that there is no inheritance of members from the generic template to the specialized template. We have to redefine the whole class. In this case, since there is only one function that is different between the templates, a better alternative would instead be to create a function template specialization. This way, we only need to redefine the print method and not the whole class. When a project grows, it's common to split the code up into different source files. In these cases, the interface and implementation are generally separated. The interface is placed in a header file that commonly has the same name as the source file and a .h file extension. This header file contains forward declarations for the source file's code that needs to be accessible to other files in the project. Remember that C++ requires everything to be declared before it can be used. It's not enough to just compile the source files in the same project. For example, if we place a function in the myfunc source file and try to call it from my app, the compiler tells us that it cannot find the function. To make this work, we have to include the function's prototype in my app. This can be made more convenient if we instead place the prototype in the myfunc header file and include the header file in my app through the use of the include directive. This way, if we want to make changes to myfunc's return type or arguments, we don't have to update every source file that uses this function. And any source file that wants to use the shared code in myfunc can just include this one header. The key idea is that the header should contain the interface of the implementation file, that is, the code that the other source files will need to use. For example, the header may include shared constants and macros. It should also contain prototypes of the shared functions defined in the source file. Shared classes, on the other hand, should be defined in the header, while their methods are implemented in the source file. The header should not include any executable statements, with two important exceptions. First, if a shared member function or non-member function is declared as inline, that function must be defined in the header. Otherwise, calling that inline function from another source file will give an unresolved external error. The second exception is shared templates. Since templates are not compiled until they are required, the implementation of a shared template class or function must be in the header file together with its declaration. An important thing to keep in mind when using header files is that any code entity may only be defined once in every source file. Therefore, including the same header file more than once will likely result in compilation errors. To avoid this problem of multiple definitions, preprocessor directives are often used to create a so-called include guard. We then enclose the header in an if not defined section that checks for a macro specific to that header file. Only if the macro is not defined will the file be included, and this will also define the macro, which effectively prevents the file from being included again.